Okay, imagine this scenario. It's 2 in the morning. You're hauling a time-sensitive load. Maybe it's pharmaceuticals. Maybe it's premium seafood worth more than the truck itself. The pressure is on. And then silence.
Yeah, that specific kind of silence that just makes your stomach drop.
Exactly. The hum of the reefer unit just cuts out. You glance in the mirror, hoping, maybe it just cycled off. But then you see the status light. It's not green. It's a solid, angry red.
You pull over, you check the display, and there it is, the number that ruins your night.
Alarm code 23.
Alarm code 23.
And that is our target for today's deep dive. We are getting into the weeds of what the manual calls a cooling cycle fault.
And honestly, for a lot of technicians, this is the nightmare scenario.
Yeah.
It's not a warning. It is a full shutdown. The unit stops protecting the cargo, period.
Right. And looking at the documentation we've got here, the code itself seems like a complete contradiction. The system thinks it's heating when it's supposed to be cooling.
It's a logic puzzle. That's really the best way to describe it.
So our mission today is to decode that puzzle. We're going to figure out why a unit gets so confused, look at the link between this code and its little brother, alarm code 21. And we're going to walk through the 6 specific diagnostic steps to get it running again. And spoiler alert, the first step involves 0 wrenches.
Which is the one step most people unfortunately skip.
We'll get to that. But first, let's set the stage. What is actually happening inside that microprocessor to trigger alarm 23?
So at its core, this is all about a temperature discrepancy.
Yeah.
The microprocessor is constantly, and I mean constantly, monitoring the difference between the return air,
The air being pulled back into the unit.
right, and the discharge air, which is the cold air blowing out onto the cargo.
That's the delta T, isn't it? The temperature differential.
Exactly. Now, if you think about the physics, when the unit's in cool mode, the discharge air must be colder than the return air. You're removing heat.
Simple enough. Cold air goes out, warmer air comes back in.
Precisely. But to trigger alarm 23, the unit detects a heating temperature differential while it is actively trying to cool.
Wait, so it's in cool mode, compressor running, but the sensors are telling the computer, hey, the air coming out is actually warmer than the air coming in?
Or at the very least, not getting colder like it should. It sees a heat rise where there should be a temperature drop. So the system says, this is impossible, something is broken, I'm shutting down.
It's like the machine knows what it's doing, but the results just don't match the effort.
And it protects the cargo by stopping, rather than continuing to run in a state that, well, that makes no sense.
But it doesn't just shut down right away every time, does it? I saw something in the sources about a precursor alarm. Code 21.
This is a crucial distinction. Typically, alarm code 23 is the escalation. It's the I've had enough phase. Usually, you'll first get alarm code 21, a cooling cycle check.
Okay, so code 21 is like a polite tap on the shoulder.
Yes. It's the system saying, hey, the math isn't adding up here. I'm not shutting down yet, but you should look at this. The unit keeps running, but it flags the event.
So as a driver, I might not even notice a code 21 if I'm not actively checking the display?
You might not. But if that condition persists or happens again after 21 is already logged, then the logic escalates. It goes from a check to a fault. And that's when you get code 23 and the engine cuts.
It's a 2-strike policy then. Strike 1 is code 21, strike 2 is code 23.
Usually, yes. But, and this is where it gets really interesting for diagnostics, there are exceptions. Times when the system skips the warning and goes straight to shutdown.
I saw that. It's like a 0 tolerance mode. When does that happen?
2 specific scenarios. First, if the unit is running a pre-trip test.
Which makes total sense. During a pre-trip, I'm asking the machine, are you broken? I don't want it to just limp along.
Exactly. A pre-trip is a pass-fail exam. You feel the cooling logic, you fail the test, it posts code 23 immediately.
Okay, so that's one. What's the other?
The second scenario is if restarts are set to disabled.
Let's unpack that. Why would restarts be disabled?
Well, some fleets, or maybe some noise-sensitive locations, they require it. You've basically told the machine, if you see a problem, do not try to fix it yourself. Just stop.
So in that case, the machine just listens. It sees the fault and thinks, well, I'm not allowed to retry, so there's no point in a warning.
Right. It skips code 21 entirely. It hits the kill switch and posts 23 on the very first occurrence.
That's a huge diagnostic clue. So if a tech walks up to a unit and sees 23 but scrolls back and sees no 21,
then you know the context. You either just failed a pre-trip or your restart settings are locked down. It helps you build that timeline of failure.
Okay, so let's talk about the human element. You see the code, the truck is silent, the first instinct is just clear the alarm and hope for the best.
The old clear and pray method. It's a classic and a terrible idea.
The sources say alarm 23 has to be cleared manually. But there's a catch, isn't there? This limited alarm resets feature.
This is what I call the anti-lazy feature. The manufacturers know people try to just clear codes. So if this feature is active, the software literally counts how many times you've cleared alarm 23.
And if you hit the limit,
If you keep clearing it, and the unit keeps tripping because you haven't fixed the root problem, the alarm gets promoted. It becomes guarded access.
guarded access, that sounds like the unit is putting up a firewall.
It basically is. It means you are locked out. You cannot clear that alarm from the standard driver menu anymore. You need a technician-level password.
Wow. So the machine says, you're clearly not listening to me, so I'm going to wait for someone who knows what they're doing.
It's protecting itself from damage. If you keep forcing it to run with a serious fault, you could turn a small repair into a catastrophic failure. Guarded access forces a proper intervention.
Which brings us perfectly to that intervention, the diagnostic procedure. There's a 6-step process here, and step 1 is data, not wrenches.
Step 1 is always data. Before you open the doors, before you put gauges on, you download the data.
The source says, download the Service Watch data logger using WinTrack.
Right. And you want to review that data using the technician user level.
Why is that so important? Why not just look at the screen?
Because the screen only tells you what's happening now. And right now, the unit is off. The Service Watch logger takes a snapshot. It records the conditions when the alarm was set and when it was cleared.
That's a crime scene photo.
Exactly. You can see what the pressures were, what the temps were, what the ambient air was doing at the exact moment the unit decided to shut down. That context is gold.
So you're looking for the trend line right before the crash.
Did discharge pressure spike? Maybe a blockage? Did return air temp plummet? Maybe an airflow issue? You can't see that in the yard.
Got it. Step 1, check the digital evidence. Now, step 2 is where we start touching the unit. Check temperature differential.
This is basically verifying the sensor data. You need to know if the computer's telling the truth.
But how do you do that if the unit is off?
You might have to clear the alarm just once and run it briefly, or just compare the sensors to the ambient temperature. You know, if it's 70 degrees outside and the truck's been off for an hour, but the return air sensor says it's 20,
Then the sensor is lying.
and you found your problem. The logic is fine, the input is garbage.
Right, because if the sensors are off, the whole delta T calculation is garbage.
Correct. You have to confirm that the heating differential the computer sees is actually physically happening.
Okay, moving to steps 3 and 4. This is the guts of the refrigeration system. Step 3, check the refrigerant level. Step 4, attach gauges.
They go together. You're evaluating the unit's actual performance, verifying its physical capacity to cool. If you're low on refrigerant, you can't cool effectively.
And if you can't cool, you might not get the discharge air cold enough, and then the computer thinks the delta T is wrong.
Precisely. It's a capacity issue pretending to be a logic issue. But there's a really specific detail in step 4 that's easy to miss. The source says, verify that sensor grades are set correctly.
Sensor grades. I'll be honest, I thought a temperature sensor was just a sensor. It works or it doesn't.
A lot of people think that. But these are high-precision thermistors. They work by resistance, and they aren't all identical. They have manufacturing tolerances, so they're graded grade A, grade B, and so on.
So the microprocessor needs to know exactly which grade is installed.
It has to. The controller has a lookup table. It says, if I see X resistance, that means Y degrees. But that table changes depending on the grade.
So if a tech replaces a bad sensor and puts in a grade B, but the controller is still programmed for a grade A.
The math is wrong. The temperature reading will be off by a few crucial degrees.
And when you're talking about delta T, a difference between two numbers, a few degrees is everything.
It's the difference between running fine and triggering alarm 23.
That's wild. You could have a perfect mechanical system full of gas, but because someone didn't change a setting in a menu, the truck shuts down.
I've seen it happen. That's why it's step 4. You have to verify that the configuration matches the hardware.
That's a pro tip right there. Okay, so sensors are graded correctly, gas is good, gauges look okay. Step 5 points us to something inside the trailer. Check for proper airflow.
This is a huge one. The source specifically calls out short cycling caused by a blocked airflow path.
Explain short cycling. How does blocking the air make the unit think it's heating?
So visualize the trailer. The unit blows cold air out the top, the discharge chute, and pulls warm air in from the bottom, the return bulkhead.
A big loop.
Right. Now, imagine a pallet is stacked too high, right up against that discharge chute.
Okay.
The cold air blows out, hits that blockage, and bounces right back down into the return intake. It boomerangs. It never circulates through the load.
So the cold air goes out and comes right back in instantly.
Instantly. The return air sensor sees this blast of freezing air and the temp plummets. But the rest of the trailer is still warm. The system sees this crazy, erratic behavior, and the delta T collapses. It gets confused.
It creates a chaotic temperature profile that breaks the logic.
Exactly. The fix in that case isn't a wrench. It's a forklift.
Move the cargo.
The unit cannot cool a box if the air cannot move through the box.
Amazing how often a mechanical failure is actually a loading failure. That brings us to the last step. Step 6. We've checked data, sensors, gas, grades, airflow. What's left?
The valves. The source says to check the refrigeration valves using service test mode.
These are the mechanical valves that control the flow of refrigerant, right?
Yes, things like the suction modulation valve or SMV, they aren't just on or off anymore. They constantly modulate to regulate capacity.
So what happens if one gets stuck?
If a valve is stuck closed, for example, the compressor might be running hard trying to cool, but the refrigerant is blocked. It can't get back where it needs to go.
So you have all this effort, but no result.
And no cooling. The discharge air warms up, the computer sees the heating differential, alarm 23.
And the test mode lets you troubleshoot this without taking it apart.
Correct. You can sit there with a laptop and manually tell the valve to open 50%, then 100%.
And you watch the gauges.
You watch the pressures. If you tell the valve to open and the suction pressure doesn't move,
Then you know the valve is physically seized. The lights are on, nobody's home.
and you found your component to replace.
So zooming out, we've gone from a truck on the side of the highway to a granular check of a single valve. It really shows how interconnected these systems are.
It does, and it shows why the parts cannon approach just doesn't work here.
Pop parts cannon.
You know, when a tech doesn't know what's wrong, so they just start firing parts at it. Replace the sensors. Replace the controller.
Hoping something sticks.
Right. But with Alarm 23, you could replace the entire refrigeration unit, and if the problem was just a blocked air chute from a badly loaded pallet, you've wasted thousands of dollars.
That's the key takeaway for me. The diagnostics are ordered that way for a reason. Data first, then simple checks, then the complex systems.
And remember that link. Code 21 leads to code 23. If you catch it at code 21, you save yourself the shutdown.
But if you're at code 23...
You have to respect the shutdown.
And don't just clear it.
Please, do not just clear it.
It brings me back to that guarded access feature. It's the machine's way of saying, I gave you a chance.
It's forcing accountability. It's protecting the asset from the human.
It makes you wonder, as equipment gets smarter, it gets less tolerant of our quick fixes. In a way, Alarm 23 isn't just a fault, it's a demand for proper maintenance. The system is designed to prevent reset fatigue.
Reset fatigue. That's a great term for it when you just keep hitting the button. But if a machine locks you out, it's asking you a serious question. Are you fixing the unit or are you just clearing the code?
The machine won't pretend it's working when it's not, so we shouldn't pretend we fixed it when we haven't.
Exactly. Knowledge is safety.
Well, that wraps up our deep dive on Alarm Code 23. We've covered the heating and cool mode paradox, the importance of service watch data, and why checking your sensor grades might just save your day.
And hopefully we've saved a few loads of seafood in the process.
Thanks for listening. Keep those air chutes clear, and we'll catch you on the next deep dive.
Stay safe out there.